Welcome to this comprehensive guide on building targeting systems and evaluating threats within Visual Studio and Unity 3D. A targeting system in game development is crucial for how players interact with the game world, influencing combat, player attention, and even auto-aiming mechanics. Visual Studio serves as an integrated development environment, or IDE, primarily for scripting and debugging, working seamlessly with game engines like Unity. Unity 3D, on the other hand, is a comprehensive game engine, providing a robust environment for creating both 2D and 3D games from scratch. By the end of this video, you will understand how to implement a basic targeting system and effectively evaluate threats using both Visual Studio and Unity. First, let's set up our development environment, starting with Visual Studio. Ensure you have the game development with Unity workload installed. Next, we'll create a new C# script directly within Visual Studio, which will be integrated into our Unity project. In Unity 3D, we begin by creating a new project. For simplicity, you can choose either a 2D or 3D template. Optionally, you can import pre-made assets like a character model and simple target objects such as cubes or spheres to populate your scene. Both Visual Studio and Unity offer intuitive code editors. Visual Studio provides advanced features, while Unity's built-in editor is great for quick edits. To make objects targetable, we'll assign them a specific tag in Unity, such as targetable, using the inspector panel. Colliders are essential for detecting potential targets. We'll use a sphere collider set as isTrigger to define a detection range around our player. Now, let's create a C# script attached to our player character to manage the targeting logic. Inside this script, we'll declare variables like target list to store potential targets, current target index for selection, and targeting range for detection. The onTriggerEnter function adds targets to our target list when they enter the player's detection range. Conversely, onTriggerExit removes targets from the list once they leave the player's range, ensuring our list remains accurate. We can implement a simple input, like pressing the Tab key to cycle through the available targets in our target list. Basic lock-on functionality can be achieved by making the player character consistently face the currently selected target. For visual feedback, we can highlight the currently targeted enemy, perhaps with a simple color change or an outline effect. Optionally, a crosshair can be implemented to follow the targeted enemy, providing clear visual confirmation for the player. Now, let's delve into threat evaluation. Not all targets are equal. Some pose a greater threat and should be prioritized. Key factors for threat evaluation include distance, where closer enemies are often a higher priority. Health is another factor. Weaker enemies can be eliminated quickly to reduce the overall number of active threats. Enemies with high attack power should also be prioritized, as they pose a more immediate danger to the player. Finally, consider which entity the enemy is currently targeting. An enemy attacking a critical objective might be a higher threat. To implement this, we'll create an evaluate target function that takes a target game object and returns a numerical threat score. We assign weights to each threat factor. For instance, distance might have a negative weight, while attack power has a positive weight. These weights can be tweaked directly in the Unity inspector, allowing for easy experimentation and balancing. A simple example formula for calculating the threat score could be threat score equals. Finally, we modify our targeting system to select the target with the highest calculated threat score from our target list. Let's explore some enhancements and tips. Consider coordination between AI units to prevent overkill, where multiple units target the same weak enemy. Influence maps are an advanced technique for threat assessment, analyzing the environment for enemy clusters and high-traffic areas. Factor in time to kill versus time to base, how quickly a unit can be eliminated versus how fast it can reach a critical location. Layer masks allow you to selectively target specific types of objects, ensuring your system only interacts with relevant entities. Remember, the best strategy can be non-transitive, meaning it depends on the opponent's strategy, adding depth to threat evaluation. Debugging is crucial. Visual Studio offers powerful tools like setting breakpoints and inspecting variables to troubleshoot your code. Visual Studio's debugging capabilities are invaluable for understanding and fixing issues within your Unity code. Its code completion and IntelliSense features significantly boost efficiency, helping beginners write code faster and with fewer errors. Visual Studio's refactoring tools can also help improve code quality by simplifying complex code structures and ensuring consistency. We've covered creating basic targeting systems, implementing threat evaluation, and leveraging Visual Studio for robust development. For further learning, explore Unity's official documentation, Visual Studio's guides, and various online scripting tutorials. Experiment with these concepts, create your own unique targeting systems, and continue building amazing games. Thank you for watching. Don't forget to like, comment, and subscribe for more game development tutorials.